remotely and at least with an online connection. I think we have another 10 there, I hope. So this is a Severo Ochoa colloquium. Our speaker today is Henri Boffin, who is also a tutor at the currently ongoing School on Scientific Writing and Communication. Very recommendable for those of you. We have already planned the repetition, so we highly recommend it. Talk to the people who've been here, they're enthusiastic. There's a lot to learn still. So, Henri comes from ESO, for the European Southern Observatory, where he's a staff astronomer and also in the user support department. And I've had great fun going. So I know Henri since many, many years, because sometimes I meet him at ESO, or I think at Chile we also coincided once. And nevertheless, I still am now going through his biography again. It has a very interesting biography. So he first did in 1993, he got his PhD at University of Brussels in Belgium. Then, and this is now a very interesting point, in 1994, he graduated from the first course of journalism and science from the École Supérieure de Journalisme de Lille in France, which is quite an interesting thing because that will become later on. We've talked about random things in careers or not so random things. So then Henri went to Japan for several years with a Marie Curie stipend. When coming back, I think it was Cardiff University first in UK, and then Henri ended up at the Royal Observatory in Belgium as a senior science astronomer. As far as I understand, it was a permanent position, so he was permanent. That was less than 10 years after PhD, so really, really good. And Henri, we were talking over dinner the other day, and then he said, yeah, I was there, permanent position, my family, that was it, basically. So now, well, it happens that then, that was just when the VLT came online, so it was 1998 to 2003 was Belgium, I think. And so ESO built the VLT, and that was like a big bang for ESO. And they were also, then at some moment, they were looking for somebody who's good at journalism as well. So Henri happened to stumble in the Messenger article over an ad, and they were looking at an astronomer, astrophysicist, who was also a journalist. And apparently, neither at ESO they believed they would find this person, but then Henri fortunately saw this ad, and now he's at ESO. So he became astronomer and in particular press officer for, I think, 10 years or longer, press officer, 7 years press officer at ESO, and now he's in the user support department and still imparts regularly talks everywhere, courses everywhere about scientific writing and teaching. So I'm doing a long introduction and I thought, now let's go to the science. So Henri has been highly focused on binary stars, and particularly very close ones, interacting binary stars, but has also gone towards star clusters, as you see, young and old star clusters and their properties, but also exoplanets and transmission spectroscopy of exoplanets. So Henri is all over the place a bit, and coming from binary stars, doing everything, and now we will talk about tidal tails and star clusters. Henri, this is for you.
Thank you very much, Anna, for this very nice introduction. You said a little bit too much about my life, that's okay. So indeed, so today I would like to talk about the arms of homoclusters. This is work that I did with Teresa and Giacomo, who are also at ESO, and also with Long Wang. So this is our place, okay? This is where we live in the Milky Way. This is a beautiful image created by Gaia. Of course, this then leads to most of the interesting questions in astronomy. So where and how did star forms that we see there? Where and how did the sun form? That's of course something that many people would like to know. And we know that the majority of stars form initially in clusters and association, and the majority of those may very quickly dissolve. Some of them are going to stay. But then the question is, how do they populate the galaxy? And those are all critical questions that many people are working on and which are interesting to look at. I'm only going to look at a very specific point of that, And I'm only interested in one kind of those clusters, which are open clusters. First, because open cluster make for very beautiful images. So, as coming from communication, this is of course something I cannot resist, to have those nice images. But open clusters are typically, so this is a gravitationally bound entity of stars that typically contains several hundred of stars, sometimes a few thousand. So much less than globular clusters, for example. Their radius is a few parsec, and they will get disrupted within 1 to 10 gigayear, depending on their mass and density and so on. And this is what I'm interested in: is how do they get disrupted? How are they going to be dissolved into the galaxy? So, but first, the question is, how do we find the member of the stellar cluster? Because of course you see this beautiful image, so you can indeed realize, okay, there must be a cluster there. But how do you know which star is part of the cluster and which star is just a foreground star or a background star? The answer, of course, is in astrometry. Okay, this is the oldest way likely that we do astronomy. Initially, it was considered to be the most boring part. Nowadays, it is so much fun. And so astrometry is simply the measurement of the position of the stars, of their motion, and their parallaxes, which means their distances. And by having these 5-dimensional properties, we can locate the star in our Milky Way, and we know exactly where they are and how they move. And of course, Henri was talking about the Big Bang for ESO, and the Big Bang for this field was, of course, Gaia. Gaia has really made a dramatic impact onto this field and many other fields, all the fields that study the Milky Way. So it was launched in December 2013 and operating, taking data from 2014. And so it has been going on for 10 years. And it is really an incredible machine that do exactly that, to do astrometry and measure the position, motion, and distance for a large number of stars. So, for example, Gaia, in the latest release, data release 3, at the position of 1.8 billion stars, and the parallax and proper motion of about 1.5 billion stars. And in addition to that, you have also the color in 1.5 billion stars, and you have also some low resolution spectroscopy of those objects, of a small fraction. So this really completely changed the field, and this led in fact to a revolution in many different fields, including star clusters. So here is in fact a plot from Castro-Girard et al. And in red are all the open clusters that were known before the Gaia release 3. And the black crosses are the new ones, which were discovered thanks to the latest data release. And so in total, we now know about 4,000 open clusters, and we certainly are going to discover even more in the future. And so we can see that we have here a completely change of paradigm in the study of open clusters. So let's come back then to this question that I raised before. How do we find a member of a stellar cluster? Because this week I am here as a tutor, I thought I will use a didactic example. Okay, so this is again one cluster, Melotte 66, which is very far away, 5 kiloparsecs away. But again, by eye, you can realize, okay, there must be a cluster there. There must be stars which belong to an open cluster. But which one do belong and which one don't? So how do we do that? So the first step is in fact that I take all the Gaia data of 1 degree field around Melotte 66, and this is about 90,000 stars. Then I can plot them in right ascension declination and also in proper motion in right ascension and proper motion in declination. And this is the distribution of parallax. And so you can already see that, yeah, there is clearly something there. There must be in the cluster. And now what we do is that we apply to that clustering algorithm. In my case, I'm using dbScan, which is a specific clustering algorithm, which is very well, very suited to study open clusters. And we do this clustering in a 5-dimensional space. So right ascension, declination, proper motion in both dimension and the parallax. And by doing this, then the clustering algorithm is going to isolate the star which are member of the cluster. And this is what we get. So we can clearly isolate the cluster, both in position, in proper motion, and you can see also in the distribution of parallax. So we managed by using the high quality data of Gaia to isolate clearly a cluster. And then we can also see at the color magnitude diagram. So this is Gaia color. This is the absolute magnitude. You can see when you have the whole thing, it's a mess. But when you have isolated the cluster, you get some nice population, single population there. It's a little bit more messy than usual. It's because this is a very far away cluster. It's at 5 kiloparsec. So there's a lot of extinction there that you would have to correct for and so on, which I did not try to do in this exercise. And we know that those clusters are going to slowly evaporating and being part of the galactic field. So how does this happen? Here I'm going to show you a numerical simulation that Teresa Jacoba did. And so it starts with a cluster that we put into the gravitational field of the Milky Way, and we just then let it evolve. So this was the initial position of the cluster. So this is in galactic, galactocentric coordinates. So this is the X, Y, and below is the X, Z. And we have then initially a well-defined cluster, and then we are just now going to let it evolve for some time. So you can read the time there on the top. And you can see that as it moves on here in its orbit on the galaxy, or here in around above the and below the Milky Way plane, it will start to develop those tidal arms because of the tidal field of that is exerted on the cluster by the Milky Way. Stars are very slowly going to drift away, and they are going to make two arms. And this is what you can see here. And so those arms will stretch out more and more as long as the number of circles around the Milky Way. So depending on the age, you will lose more and more of those stars. And so this is very interesting because then we see that all of those clusters should be indeed followed by those two arms. Some people call them tails. I think that's a big mistake. You should call them arms, because typically I don't know any animal which has two tails. Animals have only one tail. Here we have two, so those are arms. So please, when somebody talks about tidal tail, correct them. It's tidal arm. But you can see then you have a cluster and then those huge tidal arms around. And so the galactic tidal force is shaping the evaporated star into tidal arms, which are closely following the orbit of the cluster. And so what is important is that the whole life of a stellar cluster is written into its arms. And tidal arms probe also the gravitational potential of the Milky Way, and even possibly the nature of gravitation, because it's of course because of the tidal field that you form those arms, but of course also if we have a different kind of gravitation, you will need two different things. Do we have other questions, Rita?
I am always in favor of if somebody wants to ask me, I think it's more likely.
Yeah.
I would like to know that how wide the arms can be.
Yeah, I will come to
Please
that.
repeat the question.
Yes, sir.
If somebody asks now later on we will have a microphone. But now it would be kind to repeat the question so that the online audience can hear it.
So the question is, how far those arms extend on sky? I will come to that.
I'm asking because I saw in the map you saw before, there's so many open clusters, all of them have a tidal arm. I wonder if they like
They
cross
would,
each other.
Yeah, so the question is whether indeed if you have so many clusters, then and each of them has those huge arms, then of course you would start to mix together. I can reassure this doesn't happen. So they remain, the galaxy is big enough, is big enough. So because what you saw was only a plot of a projection, of course, of all the clusters, but there is of course a three-dimensional, and so most of those, so there is no much interaction, which is a pity because it would make for very nice things, because if two tidal arms of two different clusters start to interact, that would be great. But it doesn't happen, so. And so once Gaia came up, then of course people quickly realized that indeed that was a good way to study those tidal arms. And that's why there was really a flurry of paper about trying to find tidal arms around many open clusters. Here I give you a list, and I stopped in fact in 21 because afterwards the list becomes way too big and I couldn't follow it anymore. So this is corresponds more or less to until the data release 2 of Gaia. And the Gaia data release 3 was really another big bang, and that made all the things even better. But all those work was indeed all thanks to Gaia. But when we looked at those things, we said, okay, that's great. Gaia can indeed apparently allow you to see those arms, but can we do better? And the answer is yes. And this is, for example, the work done with Teresa, that she found that, for example, the IADIS and she was calling them tails at the time, big mistake. So it's 800 parsec long arms that you can see from tip to tip around the IADIS, which was really the first time people saw such wide arms around the cluster. So how do we find those arms? Okay, again, let's look at the recent example. This is another cluster, maybe a little bit more loose, because it's closer to us, and so it doesn't look so compact on the sky. And so this is NGC 752, it's 1.75 giga-year old, roughly solar metallicity, and it's 450 parsecs away. And Agawa et al. And Wu et al. Detected hints of tidal arms using the first release of Gaia. And they said, well, it looks like there is something there. Okay? And this then triggered another group, so the group by Bhattacharya, who confirmed that there is indeed some arms around this cluster. And so what they did is that they used the third Gaia data release, and they looked at a region of 5 degrees around the center of the cluster, and they used machine learning techniques in order to do clustering analysis in proper motion and parallax. And when they did that, they could see the cluster and the tidal arms going on both sides. And so they found in total 282 members on both the cluster and the tidal arms. And the tidal arms, they claim, extend out to 35 parsec on either side. And when we saw that, we said, wait, this is less than 1/10 of the IADIS. Because remember, for the IADIS, we found tidal arms which were 800 parsecs from tip to tip. So is this really all that there is? And so we need to look at, in fact, a much wider region that they did. In fact, 5 degrees is really too small. We have to look at a much wider region around the sky. And also the problem is that for extended structure, using just proper motion to do the clustering is not ideal. In fact, it's not good enough. you need to use the convergent point method, which is very old method from the 1950s, but which has gotten resurrected with Gaia, because Gaia now allows you to use it. Okay? Or you can also use even the compact convergent point method, which was devised by Teresa for the study of the ILS. So what is the convergent point method, in case you don't know? Is that if you look at stars which are on the sky, and they all move together, but if it's a very elongated structure, they will be very separated on sky, and they will also be quite separated in proper motion, in fact, because of projection effects. And so if you just do a clustering analysis in those coordinates here, well, there is no way to say that these stars belong to the same cluster as this one, because they are too far apart. But you have then to realize that if those stars indeed are moving together, then on the big circle, they will, in fact, their trajectory will converge to a given point. This is the convergent point. And so you know that there is one convergent point for every single star of this structure. And so if you now look at the great circle of your star, and you can draw a circle that goes through the convergent point and your star, you draw the circle. And then this is, for example, the proper motion of your star. You can now start to simply look at the projection along the great circle and perpendicular to it. So we have the two components of those. And if the star is indeed part of this huge structure, then it should, in fact, only follow the great circle, which means that it should have all the proper motion along the parallel plates, and the perpendicular component should be 0. And so we can now use new variables, which is in fact the predicted parallel proper motion minus the observed one and the perpendicular one. And if indeed all the stars of the structure belong to this structure, they should have those variables very close to 0. And so now you can start again to do a clustering with those variables, because they should indeed cluster around 0, 0. So we can do now the clustering no more in proper motion, but in those compact convergent point velocities in position and in parallax. There is also another way, which is to the compact convergent point methods. This is when you want to look for even further structure, because for those ones, then even the convergent point velocities are no more going to be close to 0, 0. They're still going to be also very different. But we can use n-body simulation to find relation between those velocities and see what do we predict for them to be. And so what she found was that if you would go away from the cluster in both directions, the difference between the observed and the predicted one was in fact following a linear relation. So you could remove this linear relation from the actual value and compute a new variable, which was the difference that we used before, minus this linear relation, and now it will again cluster around 0, 0. So it's again another way to find very extended structure. So we need to correct the conversion point velocities in that case, using numerical models. So let's apply this to the previous cluster that I mentioned. So if you remember, Bhattacharya were using a 5-degree region around the cluster. We decided to look at the 24-degree around the cluster, okay? And this corresponds to about 200 parsecs around this NGC 752. And now this is 4 million stars that we have to analyze. And then we use DB scan in the 5 dimension, but instead of using the proper motion, we were using the compact velocities. And we found 640 stars in the cluster and its arms. So here is the result. In the background of this figure is in fact the result of numerical simulation where we expect them, and we can see that indeed we do follow this. And so this is not the extent of the tidal arms that we found. And from tip to tip, it is 300 parsecs. And here is the distribution of the parallax. So in yellow is the cluster itself, and in green is the distribution of the whole cluster plus tidal arms. And here is the color magnitude diagram, and you can see that you have a well-defined single population there. And those are the convergent point velocity, and you can see that indeed they cluster around 0, And that's the reason why we can find them by applying the clustering. While this is the proper motion, and you can see that they are much more spread out, in fact, and they are much more difficult to find. So here's a comparison with the previous work, but there were all the color points are their points. So this is the extension of their tidal arms, and in white is the extensions of all tidal arms. So you can see that it is much spread. It's 4 times wider than what they found. That's because you have to use the correct methodology in order to find them. So it's only a careful study using the convergent point method that allows to uncover the possible extent of the arms. And this is why I often like to compare myself to an artisan. There are many people who are exploring the Gaia data by using huge scripts and getting huge catalogs. And then they have this thing that, we have found the arms of 35 parsec, but that doesn't work. You have to look cluster by cluster, very carefully, like an artisan, preparing your pasta yourself, not in the industry. And then you see much longer arms. And I hope you all agree that the taste of an artisanal pasta is often better than the one from the industry. So that's something to go for. What was interesting to realize is that the arms that we found were asymmetric. You can see that the leading arm is much more populated than the trailing arm. And this was something that was also seen in the IADIS, where you can see this arm is much more populated than the other arm. And so this is very interesting by itself. And because this asymmetry is not predicted at all by the models. And so one possibility is that it comes from the cluster initial rotation, or it might be that the cluster interacted with some massive galactic clouds, or it might also be that in fact it is the gravity, which is not correct, and we need to use MOND, so the modified theory of gravity. And there has been already a few papers by Pavel Krupa and collaborators where they indeed show that you can explain this asymmetry by MOND, and it comes naturally from their model. However, I think it's still a bit premature to do these kind of things because we need to make sure that we don't have any observational biases. So we need really to do more checks if there is any reason why we could have missed some stars there and not otherwise. So here is again the color magnitude diagram of the cluster and tidal arm, and I have now colored the stars according to their mass, and you can see the mass next to it. So the most massive ones here, and then so on. And then you can see the same color of the star here. Here you can see that in the main part of the cluster, mostly the central part of the cluster, you have mostly massive stars. So this is a clear indication of mass segregation inside the cluster. Most of the massive stars have sunk towards the center of the cluster, while most of the stars which are ejected are among the less massive ones. Those are the most easy to be ejected. And again, I had shown you before that there was some underlying numerical simulation because we wanted to make sure that what we saw was indeed close to what we should be predicted. So here is the result of this numerical simulation. And you can see that in that case, the model predicts even much longer arms, but also it predicts that the velocities, so the convection point velocities, so there will be a cluster around 0, but only for the inner part of the arms. For the other parts, they will be much more different from them. So we can do again the same thing as the compact conversion point method from Teresa and use those relations here to try to see if we can find then some other stars in the Gaia catalogue that would belong to those and see if we can find much more extended arms. And so that's why we have now looked at a region of 100 degrees around the cluster. So in this case, it was 208 million stars that we started from, which of course was not possible to give to the clustering algorithm because it's too much. And we don't have supercomputers at least. So I use models to make cuts in various variables to bring this down to 8 million stars. And then I looked at all stars that were close to the numerical model in the galactic coordinates and with convergent velocities. And in total, I got 1041 stars. And this gave me now stars which are several kiloparsec from tip to tip. So this is now the extension that we found. But you can see also in the color magnitude diagram that because several of those stars are now very far away, the precision on their measurements, parallax mostly, is not so great. So it becomes very messy here. And so that's why those are all candidates, potential candidates of stars belonging to the tidal arm of this cluster, but it will need confirmation by, for example, measuring the radial velocity, because then we have a 6th component, but also the chemistry of the star, and see if they indeed are similar to the one from the cluster. So I also looked at the Precipice, because Precipice was again studied by Rosa and Schilbach using Gaia DF2, and they found almost 1,400 stars in those tidal arms, and they did follow indeed a model, so they were convinced those are the correct ones. And so we decided to reanalyze that using again the convergent point method, the combining several methods, and this is my result. So you can see again the model is the white here, and here the white points, this is the model. So again, we are following the model. This is the cluster, and then the tidal arm expanding on. And so what is nice is to see that they follow very nicely the model here. They also follow here nicely the model, but they don't follow it here. And so this will be again an indication that something happened with this cluster. Did the cluster interact with some giant molecular clouds, or is it again an effect of gravity? And so, but the first thing, of course, is to first analyze those stars, get their chemistry, and make sure that indeed they have the same chemistry as the cluster ones, and then we know they are indeed but stars which escaped, and then we have to try to understand why they do not follow the model. So this is again the color magnitude diagram of Precipice. You can see that we have also a very nice series of white dwarfs here. We have in total 2,564 candidates, which is 1.8 times larger than what was obtained before. 1,360 solar mass in total, which is 1.7 times like before. It's covered 140 degrees on the sky, so it shows you that using a few degrees around the cluster is not going to be of any use. you need to look at huge region. And it's 600 parsec deep to deep. So it's again very, very long arms. And again, you can only find them by a careful study of these kind of things. So here is also the distribution of the stellar mass as a function of the distance from the cluster. So this is the inner part of the cluster going from 0 to 12 parsec. And so you can see that you have again mass equation. The most massive stars are in the center of the cluster, and then it level off. While at the arms have indeed mostly composed of lower mass stars. Again, those are only candidate stars. So you want to check whether they can be a real number. One way to do that is again to look at the radial velocities. So only for a subset of those do we have radial velocities. And for those, this is here the radial velocity as a function from the cluster. Again, the white points in the background, this is the model, and you can see the measured points. And you can see that the good thing is that we do follow this part here. We also do follow for that. There is here a set of stars which do not follow, and so they could not be, potentially they are not members. The good thing is that most of them, in fact, they are shown in red here, and so most of them are in the inner part, and so they would not say anything about the extension of the arms. They don't change this conclusion. But of course, also here it's dangerous to use those values because for most of the stars, we have only one radial velocity measurement. And if those stars are binary stars, which many of them are going to be, then of course you cannot use a single value of a radial velocity. You need to take many and then take the average, because depending where you are on the orbital cycle, you will get a different radial velocity. Another way to check whether they are indeed member of the initial intercluster is to look at their metallicity. Unfortunately, for most of the stars, we don't have spectra, but we have the Gaia low resolution spectra, and Henri et al. Derived from those using machine learning techniques. They could derive, in fact, metallicities. And here again, I have put the points for which I have this value colored. So here is 0 is solar metallicity. This is plus 0.2 and minus 0.2. And you can see that most of the stars are indeed with solar metallicity, so in agreement with the cluster. And this is in position, this is in conformation. And you can see that even in the where they are very far away, they are still in this range. So this seems to be a very good indication that indeed those are real members from the cluster that were ejected. And this is the distribution of the metallicity. But the metallicity is of course only one very generic thing. So now what we need really to do is to go and look at those stars, take a spectrum, and measure the abundance of all the other elements and confirm that indeed they share the same abundance pattern as the one from the cluster. But this is of course a very long-term effort because you need to take spectra of many stars. So long arcs have been found for 4 open clusters now. Here I show 3 of them. And we are now in the process in looking for arms around a large sample of open cluster. But again, I refuse to do that in an automatic way. And I do that really as very manual work. I can allow myself to do that because I have a permanent position. And this is in fact all the clusters that I've been looking at for the moment. So already quite a few. And you can see that in most cases, in fact, we don't find any tails or arms. And so we have only a handful of candidates here. So for example, in this region around LGC 2358, so here you can see in galactic coordinates several clusters, and there is no apparent indication of arms on those ones. This is a region around something I'm not going to tell you, and there we have a very nice candidate. of a cluster which has very long arms, which we are studying for the moment. Here for NGC 2423, we do have some kind of small elongation, so very small tidal arms only. And so the idea is also that by combining the study of so many clusters and see what is the extent of the arms for all those clusters, we are going to try to do correlation with the age and the mass of the cluster and their position in the galaxy to see how this influence, in fact, the size of those tidal arms and understand then how do stars indeed dissolve into the Milky Way. So here is another cluster, UBC 274, which is very far away. And here we do see long arms, which seems to extend over several hundreds of parsec. And when we look at the color magnitude diagram, it looks rather good. But in this case here, I'm a little bit worried because unfortunately the precision in the distance for most of the stars is of this order of hundreds of parsec. So it's a little bit dangerous to claim that we are seeing them in this case. And the problem is that if a cluster is farther out, then the parallax is smaller, of course, and we have a relatively larger error on it. But also the stars in the arms, as I told you, are the less massive ones, which means they're also the faintest ones, which means that they're even fainter than the cluster. And so you have even more larger error on the parallax and on the proper motion. And so starting to do clustering analysis on that is of course very dangerous. And so for those kind of clusters, we will need to wait until the next Gaia release DR4 and then finally DR5. So DR4 is supposed to come in 2026, while DR5 will be after my retirement. So I will have to play only with DR4. So I conclude by giving you the recipe for finding tidal arms. You should start with a wide enough region around the cluster. Don't limit yourself to a few degrees. Go bold, you go to 20, 30, 40. Use the convergent point variables in the clustering and not the proper motion. Combine different methods because that's the only way that you can have the full extent of the arms. And compare to n-body simulation to make sure that indeed what you find are not just random stars, but are indeed where they are predicted to be. And once you do that, then you indeed find that the arms of all the cluster are much longer than thought, much more difficult to find. Thank you very much.
Thank you very much. Very enlightening. So I agree with the artisan approach often because I mean people ask me, oh, you astrophysics, all artificial intelligence, and I say, no, but we need to understand the data before we can do anything intelligent with it. So are there questions? And John, yeah, please wait for the micro.
Okay. Thanks a lot, Henri, for the talk. I have realized that you really follow in your talks your recommendations. It was really very easy to follow and I have enjoyed very much. Let me ask you a second curiosity, in fact. Can you elaborate a little bit more on the asymmetry of the two arms? Is there, I mean, you said that we have to be cautious in the sense that there are still observational biases we don't understand, but is there any physical reason you can think of for this? I mean, you mentioned some possibilities, but if you can elaborate a little bit more, I would appreciate it. Thanks.
Yeah, so in fact, here, of course, what we do in the numerical simulation is that we take a realistic potential for the Milky Way, the one from Henri et al. And so it's supposed to be very realistic, but of course it is symmetric. And then what we do is that we then have a cluster moving into the potential. But what we don't do, for example, is to include also all the potential interaction that this cluster could have with other things that are in the Milky Way, like giant molecular clouds also. And so, or in fact, it's very interesting that the ESA press release onto this paper about the iodis and the asymmetry, they mentioned the possibility that the cluster could have interacted with, for example, a small lump of dark matter, if they exist. So if there is some lump of dark matter in the galaxy, then it might be that the cluster came too close to that, and then the tidal arms would become deformed in this sense. So we don't know that. We tried some. So we have done one simulation where we did try to have some kind of close encounter between a giant molecular cloud and the cluster, and we do indeed see those asymmetries appear. So that's one explanation. Which of course, the problem is that we could not find in any catalogue any molecular clouds that would have been close to the trajectory of the iodis. And so, and that's why when people say, well, then maybe it's because it's a clump of dark matter. And that's why it was it. But of course, it starts to be stretching a lot. And so the other possibility, and this is what is followed by Pavel Kupa and his team, is that you have a different kind of gravity. And in that case, you have modified Newtonian gravity. And then they made some simulations. And then, in fact, they say that indeed, depending where you are in the orbit and at what time you are, because there you don't have any more this symmetry, then you can explain, in fact, the shape of the three tidal arms that we have seen. But as I mentioned, the problem is that, I mean, you have already seen, I mean, people claim they saw some arms. And then we come in and we do the artisan work and we find longer arms, much longer. But we never say we are complete. I would not dare to say that. There is no way I can know that. Okay? There's no way. The only way to know that we are really complete is to observe all the stars in all this region, take a spectra, and confirm that they are indeed coming from the Earth. That would be the only way to know that. So we don't know if we're complete. But one of the things that we plan to do is, in fact, because there is a simulation catalog of all Gaia data, so we are going to use that and apply the same method that we use on real data to those simulation data, and see whether if we dare put artificially or numerical model, would we indeed retrieve the full thing, or would we retrieve only part of it? So this is something we plan to do. I hope I answered your question.
Ruben?
Well, thank you very much for the nice talk. I wonder what can we learn from the formation of these clusters, like star formation regions. A follow-up question to that is, what should we observers be looking at star formation regions? Because I think the properties are very different from protoclusters and actual clusters.
Yeah, exactly. So this is also why here, one of the things, here I'm looking at open clusters, so they're really well defined. I mean, they're very well established and they're actually old. But in fact, we also look at some of the younger open clusters. And then, in fact, this is where, for example, again, Pavel Kupa distinguished two with Frank Didier, they distinguish two kind of tails. Again, they call them tails and not arms, which they do. But so there is the tidal tail 1 and the tidal tail 2. And the tidal tail 1 is in fact the one that you will have from the initial, when you have your initial cluster, then of course you have all those massive stars that are going to be there. They're going to evolve very quickly. They're going to make supernova, strong winds, and so they are going to also inject all the gas. And so the cluster, which was initially maybe more compact, will extend in fact. And that it will become elongated, and that's the first kind of arms that we have. And so this is what we see in some of them, very young ones. We see this very short elongation, which is not the full tidal tail. To have the full tidal tails, you need really to to at the start we have at least done one half of our rotation in the Milky Way. So at least 100 mega year or so is needed before you can see that. And so that's the thing, is that by looking at the tidal TS1, we can really then tell, hopefully, what happened to the initial cluster. Okay? Why did it get deformed like that? And this is what we try to see. I don't know if I answered your question, but that's all I can say.
Thank you, Henri, for the talk. I have rather a technical question. When you use DB-scan, what method do you use to constrain the epsilon distance?
Yeah, that's exactly one of the things why I say we are artisan in that sense, because we refuse to choose one epsilon, and we also refuse to choose one n, so the size of the n sample. What I do is, in fact, I do a parametric, I do a full search in this two-dimensional plane. So I look for all the possible values of n samples, all the possible value of epsilon. And then I select, in fact, all the stars that will give me the longest arm. So I don't have a value a priori, but I try them all, and then I choose again the best one, which is again different from what most people do. Most people will use HDB-scan, which I guess you know.
No, I use DB-scan too.
Okay, but most people will use HDB-scan because then you get rid of this epsilon. You have only one parameter.
Yeah, exactly right.
So,
So
but I don't think it's a good idea, because what we see is that indeed this epsilon will really depend on the precise cluster.
Okay, so for example, if you have a very clear cluster concentrated on dense,
Yeah.
you still use that method.
Yes, we will use that method, but of course we renormalize all the time the variables. So, for example, if you have something very concentrated, we use the standard deviation of all the variables to normalize all variables. And so at the end, we always have only numbers between -1 and 1.
Okay, I'll ask one question. The all variables you use to look for the cluster using DB-scan, do you weight all of them equally, or do you put more weights on the proper motion or the position?
No. Yeah, exactly.
Or is it all of them are equally important for you?
For us, they are all equally important, and so that's why they are just all renormalized. And so E-log will always be divided by the standard deviation. But we don't try to weight them. But on the other hand, this is what I mentioned when I say we combine different methods, is that the usual method is to use, in fact, the conversion point velocities with the galactic position. This is our standard method. But in some other case, we in fact combine those compact point velocities with the galactic coordinates and the distance. And in other case, we are using the compact convergent points. So we combine also several methods. And that's what you could see for sorry. Yeah, here you can, that's what you can see for parsecs. Those are the different methods that we use. And you can see that, for example, if you use a normal clustering in 5 dimensions using only the right ascension, declination, proper motion, and parallax, then you get the red points. So you only have the central part, so you have the cluster. But then we can use the conventional point velocities. This is what gives the green points. And if we use the convergent point, we have the purple points, which extend more. So we try several of those methods in order to see how far can we go.
Okay. Thank you very much.
Can I add a technical question also? Question. Can you briefly review the convergent point method? For some reason, I got a bit lost there. And I don't know whether is it because the cluster are very near and cover a very broad area on the sky, so if they were very far away, I wouldn't need that, or is it?
Exactly, that's exactly that, is that if they are far away and they are, then, I mean, this is exactly the first example I showed. So Melotte 66, it is so far away on the sky that indeed it looks like a lump, because
Okay.
the physical extent is always the same. So of course, if you put it further away, it will look much closer, and you don't need to look for a huge region. But the problem is that those which are far away, they have very less precise parallax and proportion.
And when I have a large angular region in the sky, I don't have apparently aligned proper motions anymore.
Exactly. And that's the case, for example, the INDs, you really have to look at basically 180 degrees. And then the proper motions, they're just projection effects.
Okay.
They do not align with
Because
those.
we look at the galactic center, the 8 kiloparsecs.
Yeah, they are always more, then you don't need to bother with that.
I have another question.
Who was the other question?
I'm looking for cluster too, but it's not working right now. Hola? Yeah. So I look for cluster two in the galactic center, so everything is so messy. So I'm afraid I only can look for the cores of the clusters.
Okay.
I mean, I don't think I want to be able to find any arms or whatever in this region. But do you have an idea how the velocity of you saw that the more massive stars are, the more much concentrated.
Yes.
So do you have an idea how time is going to affect the proper motion, the variation in proper motion of this core in clusters, or are they? I assume they are going to be concentrated in proper motion longer, right?
Exactly, they will be, I mean, you don't have this problem of projection effects because they are so far away. So it should not be a big problem. I don't think that in this case you need to use the convergent point velocities.
Yeah, I mean, I'm looking for any possibility.
I see.
Yeah.
Yeah, but I don't think this would help in that case.
Yeah.
You really also need to see, because you see again, if you don't use the convergent point, then you have the result from Bhattacharya. And this gives you an extent which is about 10 degrees at most on the sky. While with the convergent point method, then you have now more than 30, 40 degrees.
So
But in your case, this doesn't matter. They are even much closer.
So you will say that at least in these cases, in these open cluster cases, the last remainder of the cluster will be the more massive star, right?
Yes. If it's old enough that there was some mass segregation, yes. Really.
Okay, thank you.
Which of course also means that if they are very massive, well, it depends on how old is your cluster. Of course, we also know that the more massive stars are our in binary system. And if they are in binary system, then of course your proper motion is going to be affected by the motion of each product.
Yeah.
So there again, you must be sure that you use a kind of a mean over a long enough period to get rid of this orbital motion.
Hello, okay. So I have this question. In one moment, you said that that the asymmetry seen in the arms of the open clusters could be due to the interaction with a lump of dark matter.
Yeah.
So I have this problem with dark matter. So obviously there is more dark matter than, let's call it, regular matter. Okay, light emitting matter or baryon.
That's the standard model. That's not what Pavel Kuba would say.
Yeah, I mean, I don't know those theories. So it saves the large structure of a galaxy in the universe, and obviously there is a matter we are not seeing, at least for the standard model what I have learned, because then the rotation cubes of galaxies couldn't make any sense. But I have this problem. If it is so massive and it's so present, why do we never see any direct interaction between baryonic matter and dark matter in terms of gravity? For example, here you have these open clusters with these wide arms. If dark matter is so present, why don't we see any small scale interaction like these very extended arms interact with one lamp, because it reminded this asymmetry wasn't very pronounced. It was somewhat subtle.
Well, no, it is statistically significant.
It's
Yeah,
significant.
we clearly see in 3 cases, we clearly see that the leading arm has many more stars than the trailing arm. And that's, I mean, at least for 2 cases, it's statistically,
Okay.
it's not subtle.
So, yeah, then this changes a bit my question. Well, basically, could be the training of the arms, or at least the space they are swiping, let's call it that way, could be used to study the extension of dark matter, because we never see them interacting, but it has to be somewhere.
Yeah, exactly, but that's the hope of this whole study, is that by studying in details those tidal arms and making sure that we have the full extent, and that we have exactly the real composition of both the leading and trailing arms, we can then have a real observation on quantity that we can compare to the model, and then in the model we can start to put more lumps of dark matter, or we can put modified gravity or this kind of thing, and then we can see which one is better. So, and this is exactly what Pavel did, and that's why he claims that he has a good agreement with the modified Newton dynamics. He can explain what we see. So that's really what we have to do by adding even more and see whether indeed that's the only explanation, or if we can do some other. So some other people, for example, also say that they could be the influence of the stellar bars. Okay, we know that in the center of the Milky Way there is a stellar bar, and this bar is of course rotating. And so it might be that it is simply the differential rotation of this bar that is also introducing some kind of asymmetry. And this is also something we have to put into the models to check whether indeed this could explain any asymmetry. So that's why I think we are still at a very early stage. My point is only to show that now we can start to see really long arms, and so we can hope to see the full extent of them. But we are still in a very early stage, before we can really compare these models.
Thank you very much.
There is an online question by Soulmate Queen, so if you can open your mic. Soulmate Queen, can you open your mic and make your question?
Hello.
Yeah.
I have a quick question about the input parameter of the embodied simulation. So how did you get the initial cluster total mass for those clusters for your embodied simulation? Because the cluster member we saw today with Gaia are different from when they were born, right?
Yeah, you are totally right. I mean, especially a cluster like HCC 752, which is already 1.7 giga old. I mean, this is what you can see in the here, for example, in the color diagram. You can see that we are left only with stars which are up to 1.74 solar masses. All the other stars, they have of course already evolved and they're becoming either white dwarf or black hole. So we have lost a lot of mass there. So that's why for the moment we did not try to really fully reproduce the current mass of the cluster because in fact we were unable to. So what I did was that I did a simulation by starting from a cluster which had initially 5,000 solar masses, and then at the end of this 1.75 gigayear, I obtained a cluster which was about 2,000 solar mass, which is too big compared to this current cluster. The problem is that the current cluster that we have there is less massive. It's about 800 solar masses, and if you look at numerical simulation, there is no way that you can make a cluster that can survive for 1.7 gigayear and have only 800 solar masses. Such a cluster should have been already dissolved much faster and should no more be there. So that's one of the big problems that we have now, is to try to understand why is this cluster there? Because it should not be there, according to the numerical models. So it's a great question indeed.
Okay, thank you. And I have another question. What's the typical physical size of the tidal arms for the cluster you have found?
Yeah, so typically it's a few hundred parsecs, so it's really extend from tip to tip is between 200, 300, 400 parsecs, and then the IDS is even the biggest one with 800 parsec. But again, the reason why we see the full extent of the IDS 800 parsec is because it's so close to us. And that's why it makes us think that, of course, all the other ones, and indeed, that's what the numerical simulation show. The numerical simulation show, and by using the convergent point method, there we have even ints of arms which spread over several kiloparsec, and that's what they should do. But of course, with the current Gaia data, it's very difficult to improve that. So that's why we hope with a new Gaia release that we will be able to find tidal arms which extend over several kiloparsec.
Okay, thank you.
Okay, I think time is advanced, so Henri will still be around until tomorrow. So, any further questions? I think we can approach him. Thank you very much. Fantastic talk.